we just had a quiz where we were trying to find the volume of a sphere, which, well, there it is, but we wanted to actually prove that. Okay, so I'll give you one method of doing this. So simply take a circle, right, with radius r, but don't draw the bottom half, right? So we just get the semicircle. So here you have the top half of a circle with radius r. Okay, now remember, a circle is given by x squared, at least one centered at 0, x squared plus y squared equals r squared. If you want to solve for y, right, so you could write this as y equals the square root of r squared minus x squared. Okay. Now, this should be plus or minus in general, right? But since we're looking at the top half of the circle, we just take the plus part. Okay. And now the reason why we do this, and we, of course, bound it by that function, right, and the x-axis, right, which is y equals 0. And if we take this region and we rotate it around the x-axis, what will we get? We get a sphere with radius r. Right, just rotate it around. There you go. There's a Ah, very good. Well, of course, you could also do a half circle this way and rotate around that axis. Okay. So since we have a function of x, which we rotate around the x-axis, there's just one variable, so we use the 1 pi formula, right, which is the disk method. Okay. And so the volume, right, would be pi, right, one variable, 1 pi, integral from minus r, right, so this intersects at r and minus r to r of the function. Okay. But it's not really just the function, is it, right? Remember, this is the pi formula. It came from pi r squared. So that means you have to square this thing. Okay, so the volume is given by that. Now, there's a little simplification you can make, okay, to make things a little nicer, which is if you rotate this entire semicircle around, you'll get twice as much as if you just rotated one of these quadrants around. So a half of the volume would be given by, well, just integrating from 0 to r of the same thing. Okay, of course, when you square the square root, it goes away. And the reason why this is maybe a little nicer is you have a 0 now. And so when you plug 0 in, usually things will die nicely. And in this case, they will. So here you integrate r squared with respect to x, and you get r squared x. And the integral of x squared is a third x cubed. And then we'll evaluate at 0 and r. And like we'd hoped, when you evaluate at 0, this is all going to die. So you just have to evaluate at r. And when you put it in r, you get r cubed minus a third r cubed. And so that's, well, 1 minus a third is 2/3. Pi r cubed. Since that was half the volume, the whole volume is 2 times it, or 4/3. Pi r cubed. So this is nice. We now offer a very nice proof of the volume of a sphere. Note that this is actually easier than the area of a circle calculation. When we did the area of a circle calculation, there was a square root, but there was no square. Right? And so it was harder to integrate. You had to use trig substitution to do it. So this one, the volume of the sphere is actually easier. Okay. Any questions about this? All right. Last time, I think we didn't quite finish all of the volume stuff, including the rotating around a different line, x equals -2 or y equals -2, one of these. Well, we're going to pick that up again tomorrow, along with looking at volumes of some region where you know the area of a cross-section. But right now, we're just going to talk a little bit about polar coordinates, which is what's showing up on the homework. And there were some questions from people in the other class about what this polar coordinate stuff was. remember there's a reading that you can look up for these things. But in case it's a little too complicated in the reading, let's just quickly go over the basics. So maybe one way to motivate this discussion is to go back and remember our alternate way of defining cosine and sine. Right? So remember what we did? We drew a unit circle. Okay, so here's a circle with radius 1. And you choose an angle, theta. And now you get a right triangle, right, by taking, take this ray which goes from the center of the circle to the circumference of the circle, and then drop a perpendicular to the x-axis. Right? And along with the x-axis, you get a right triangle. And so, right, if this coordinate, the coordinate of that point is x comma y, then we know that, right, let's write it like that. Right, the base of this triangle has length x, and the height of the triangle is y. Okay. And then the hypotenuse of this triangle, well, remember the hypotenuse, actually here's just the radius of the circle. So that's 1. And what's really nice when you have a triangle, right, with radius, with a hypotenuse 1, is that the cosine of this angle is just the adjacent over 1. So it's just the adjacent side, so it's x. So that x is actually just the cosine of the angle. Right? And the sine of this angle is just the opposite over 1, which is just y. So, right, remember this is picture we drew last term, and this gives you an alternate way to define cosine and sine. Right? Instead of basing it off of the right triangle, right, for any point on this circle, you define the cosine of the angle that you get as just the x-coordinate of that point, and the sine of that angle to be the y-coordinate. And, well, since we know that this circle is given by that equation, this, of course, gave us that cosine squared plus sine squared equals 1. Right? So this was a very nice way to do things. Okay. Now, let's say that we had, instead of starting with a unit circle, we had instead started with just an arbitrary circle centered at 0. Okay, so let's we're going to draw the same picture, only now my radius is going to be r. Okay, and again, this could be the x-coordinate and the y-coordinate, and that'll be x, and that'll be y. And if that's theta, what will cosine of theta be? Cosine of theta, the adjacent over the hypotenuse is x over r. And so if I just want x, right, because I have an x here, I can rewrite it, x equals r cosine of theta. And similarly, right, well, sine of theta is y over r, so I can solve for y. Right? So y equals r sine of theta. And so I can now write this as r cosine of theta, r sine of theta. Now, what's really nice on this right side is that if I tell you what r is and I tell you what theta is, then you can compute the cosine of theta, you can compute the sine of theta, you can multiply them by r, and now you know exactly what point you are in the plane. So what this gives you is actually a way to change your coordinate system. Instead of specifying where you are in the plane by giving a point as far as x, y, right? How many units along the x-axis and how many units along the y-axis. Instead, I can give you this number r, which is the distance from the origin to your point. And I can give you an angle theta, which is based on, right, the angle between the x-axis, right, and this ray that would go out to your point. So it's just a different way of specifying points in the plane. Okay? So it's just a different way of giving coordinates. Okay? So the relevant equations here are 1, x is r cosine of theta. Okay, if you want, this is for how to transfer back and forth between what we call these x, y coordinates. These are Cartesian coordinates after René Descartes, but they're not called Descartesian coordinates for some reason. Okay. And the y is r sine of theta. And, well, a couple other useful formulas here that you can get from just the triangles we've drawn. First, what is x squared plus y squared? So x squared plus y squared equals r squared, right? So it's the Pythagorean theorem. Okay. Okay. And also, if you would like to talk about this angle theta and y and x, but not have to talk about r at all, right? Because somehow you should be able to do all those without talking about r. Well, notice if you want to say something about this triangle, right, say using trig functions, that doesn't involve r, what trig function might you use? Something that doesn't involve the hypotenuse. You could use tangent, right? Okay, what's the tangent of theta? Right? Opposite over adjacent, right? Y over x. So this is also useful. So if you use these equations, you can pass back and forth between the two systems of coordinates. Okay. Now let me give you something a little more tangible here. So let's do an example. Okay, so let's plot the polar coordinate. So let's plot the polar coordinate. Well, the way a polar coordinate is given is not as an x comma y, but as an r comma theta. Okay. So I have to give you an r, and I have to give you a theta. So let me give you 2 comma pi over 3. Don't even, I mean, we'll do that in a second, but here we just want to plot it. So what we're going to do, right, well, actually usually don't draw this, you actually usually start with the y-axis in there. Okay, so you just start with, well, you'd call it normally an x-axis, but when you're talking about polar coordinates, you call this the polar axis. But it looks just like the x-axis. Right? Okay, and we fix a point. Again, you might call it the origin or the polar origin. Okay. And now what we're supposed to do is plot this coordinate. Well, this pi over 3 tells us the angle that we're going to have to go up. Okay, so we start here, and we go up by pi over 3. Like that. Okay? So we're going to make an angle here, and that angle is going to be pi over 3. Okay. Now the question is, right, so you start with a ray at the center here, and you go out. Okay, and how far do you go out? You got 2 units, right? Okay, it should be 2 units away. Okay. Now, when I plot this, this line is actually not the plot. Okay, this just is a reference here so I can see where it should be. The point is right there. There's the point, 2 comma pi over 3. Okay, so actually, in the end, right, you get rid of that line, right? You can just, it's hidden in the background. Same thing with that angle. Okay, that's the point. Okay, now, who was it? You, Chris, you were asking, let's convert this to polar, or to rectangular, Cartesian coordinates, or, by the way, sometimes in this context, they're also called rectangular coordinates instead of Cartesian coordinates, but either one is fine. Okay, so how do we convert it back? Well, in rectangular coordinates, okay, well, we have these formulas that tell us x is r cosine of theta. So x is 2 cosine of pi over 3. And y is 2 sine of pi over 3. Okay, so let's see, cosine of pi over 3. Well, pi over 3, let's see, it was 0, pi over 6, pi over 4, pi over 3. So the sine is root 3 over 2, and the cosine is root 1 over 2, or a half. So this is 2 times a half, which is 1, and this is 2 times root 3 over 2, which is root 3. Okay. So in rectangular coordinates, 2 pi over 3 becomes 1 comma root 3. Okay, so this is the polar coordinate. This is the rectangular or Cartesian coordinate. Okay, now you might be asking, why? Why are we doing this? Are we really just masochistic? Why would we want to make things more complicated? Do we really need another coordinate system? And the answer is yes. Yes, we do. And no, it's not that we're masochistic. In fact, we're lazy. We want to simplify things. And it's going to turn out that in many cases, the way to take a problem which looks very complicated is to turn everything into polar coordinates. And once you do that, things look a lot easier. Okay? And let me give you a quick example of something that looks a lot easier in polar coordinates than it does in rectangular coordinates. Oh yeah, you can get some real funky shapes very easily. Oh yeah. All right, well, let's get a nice funky shape really easily. Okay? So let's start in rectangular coordinates. Okay, this is supposed to be a circle centered at 0. Okay, what's the equation of this circle? Say it has radius r. Here, let me make it even easier so you don't have to worry about these things. Let's make it 2. Okay, this circle is radius 2. What's the equation of this circle? X squared plus y squared is equal to 4. All right? And when you want to start manipulating these things, solving for y, then you get all this nastiness, right? Y equals the square root of 4 minus x squared, plus or minus, really, to get both sides. Okay? It's not even a function, right? I mean, it's just some nasty equation. Okay? Let's do this in polar coordinates. Okay, so this is rectangular. Let's do this in polar. somehow I want to write this down as a nice function here. Okay, again, with radius 2. I want to do this in polar coordinates. Well, let's see. What if we try to convert this? Let's look at over our formula list for a second. Okay. X squared plus y squared equals r squared. So it tells you what r should be. 2. Okay, but we guess we kind of knew that, right? The radius of the circle is 2. Okay, so the radius is 2. But now what happens in this circle? Well, you start off, say, right? Say you take this point. Okay, what's the coordinate of that point in polar coordinates? Well, the radius is 2. What's the angle here? Don't worry about sines and cosines. You're overthinking it. What's the angle here? 0, yeah? And let's say you went up over here. Right. Say this is at 45 degrees, right, or pi over 4. What's the point? 2 pi over 4. And if I went up here, it'd be 2 pi over 2. And say I went over here. What do you think? What's the radius out here? You go out 2 in the pi direction, right? You go pi, and then you go out 2. Okay. I know, of course, it looks funny, right? You think, wait, hold on. Shouldn't that be a negative number or something, right? We'll talk about that in just a second. Okay, but this angle here is pi, right? You go out over pi, and then you go out 2. Okay, so that's the coordinate, 2 pi. Okay, and if you went down here, two, 3 pi over 2. Okay. Do you notice something very special about the first coordinate here? It's always 2, right? And I can put in any angle, and it's going to give me some point on the circle, right? What happens when I go back to here? Well, it goes up to 2 pi, and I can actually keep going around. But it's always just going to repeat things on this circle. Okay. So this circle actually represents the set of all points which are exactly 2 units from the origin. Okay, it's all the points that are 2 units from the origin. Okay, go out in any direction from the origin, right? You go out 2 units, boom, you're on the circle. Which means that right there completely describes the circle in polar coordinates. Okay? Instead of having this thing, which gets really nasty when you start fiddling around with it, right? And especially when you start moving, right? This r equals 2, boom, you automatically got it. And if you wanted a circle with radius 5, what would the polar equation be? R equals 5. Okay? Just all the points with radius 5. You don't care about the angle because you get them all. Okay? So you can already see this. I mean, this is really much simpler. Yeah. Okay, but we're going to get to see a little bit this term. Those of you who stick around for multivariable calculus next term, we're going to be using polar coordinate transformations up the wazoo. They're just all over the place. Okay, let's see. We got just enough time. So I wanted to say one more thing, which is, of course, there's no such thing as negative radius. Yeah? But we do define polar coordinates with a negative number in this first component. Right? And the way we do it is as follows. Okay, so let's say I don't really need a circle here, so let me redraw this without the circle. Let's draw our polar axis. Right. And I'll pick an angle. Let's say theta. Okay. And I'll pick some point, right, going away, and that's my radius now. So the coordinates here right? If the radius from there to there is r, then the coordinates of this point in polar coordinates is r comma theta. Okay, and here we take r to be greater than 0. Okay, now what if I wanted to make r less than 0? Well, here's all we do is we just go out r in the opposite direction. Right, so we'll pick whatever that distance is. Okay, so that distance is again r. Okay, we go in the opposite direction of the angle. Okay, and we'll call that minus r theta. Okay, now what is usually very tricky about this conceptually is, okay, I've drawn this really nicely where the minus r seems to be below the polar axis. Okay, but what if instead I had drawn this? Okay, here's my polar axis, and now here comes my angle. Okay, okay, there's my origin, say. Okay, so it's this whole thing here. So I actually get, it looks like this, right? There's my theta. It's this whole angle. Okay, and here's my r. Okay, so again, r is greater than 0 here. Okay, so this is the point r theta. Right, because I go around theta and out r. But now if I want to do minus r theta, I have to go this direction. Right, I take this distance. Okay. There's again r. But now, because my theta was all the way over here, I write this as minus r theta. Okay, so that all you do to get a minus radius, okay, is you just take this line that you get, this ray, and go backwards on it, go in the opposite direction. Okay? But that means is you can get these minus numbers in the first component up here, right, above the polar axis, which is a little counterintuitive. But remember, we're not in the Cartesian system anymore. All right? This doesn't mean you have to go to the left. Okay? In the same way that you can put a negative angle. By the way, what do I mean by a negative angle, you think? Yeah, just go the other way. Right? So if I went down here, right, then I could go, if I go this way, I could have negative theta. Okay, and so this point would be r comma negative theta. No? It's kind of weird, right? Yeah, it takes a little practice. It's not negative r because we're going, that's our angle, and then we go out that direction. Right? Here was, remember, well, actually it should be out a little further, shouldn't it? But, there we go, to be the same. Okay. So first you do your angle, and then you go out your r. If I was going to have a negative r, right, then it should be going that way. Okay, and then have it over here. Right, so up here, that point should be symmetric, right? That would be negative r, negative theta. Okay. Okay, now this, like I said, this takes some practice, right? But it just takes a little bit.